let me know if you can't see the screen. But yes, so this is a greedy algorithmic problem. So we haven't covered much about greedy algorithms, and essentially greedy algorithms are an approach of solving a problem by finding the locally optimal point in time, and by trying to find a local optimal solution, you'll eventually be able to approach a global solution to this problem. So it's not as difficult as it sounds like, and I think it's a useful approach to practice. So this is a problem that we'll be practicing a greedy algorithmic approach to. So this problem is container with most water. So given a list, given an input of, say, a list of integers, each integer value represents the height. So just think of this as a histogram. And our goal is to find the biggest area, or the container that can hold the most water between two of these bars in this histogram. So a brute force solution, and you should already be thinking about this, is just to do a double loop. So we loop through every single height, we loop through every single integer in this list, and then for each of the integers that we loop that we're currently on, we have an inner loop in which we loop through every other single integer in the list, and we just calculate, and then we calculate the max area of all of these combinations, and then we return the biggest area among them all. So this solution would take O of n squared time, because you have an outer loop and you have an inner loop, and that's the brute force approach. So that is the naive solution, and that isn't something that is too complicated. So our question is, can we devise a solution that is a lot more efficient, that we could just do it in essentially with one pass? We don't have to do an inner loop. So that is, so we'll be using pointers or counters. So we would use intermediate variables to track the max area. And what I'm thinking that we can do is we would track the leftmost index and the rightmost index. And then every single time we approach a bar that's bigger than the rightmost index bar, let's say we start with the left index and we hit this, and we increment the left index to this, so now we're currently on the second bar, and then we're comparing it with the right index. So for this particular problem, we don't even have to increment the right index at all, because you can see that the max area is the area that encompasses the one in index position 1 and the last index position. And you can see that the max area that this container can contain is 49, because the x, so this is 1, 2, 3, 4, 5, 6, 7. So our width is 7 and our height is 7. Very important to note that since we're trying to get the container with the most water, our water cannot overfill. So even though we start with the index position 1 that has a height of 8, we're choosing the minimum between the 7 and 8 so that the water does not overfill. So basically, by incrementing the leftmost index and comparing the size of the rightmost index, you can see that if our leftmost index is bigger than the rightmost index, we can keep, we don't have to worry about the other bars that are smaller than the leftmost index that we're currently on. So we just skip the first bar, and we can keep incrementing as going forward until we find the maxed area. But you can see that the maxed area here is already as big as it gets for this particular example. So maybe this example isn't the best one, but hopefully that elucidates the approach a little bit. So let's actually implement it. So let's actually keep our pointers. So let's track our left index and our right index, and also our max area. So our left index, of course, starts at index position 0. Our right index is the length of the list we're given, which they call height. So that's the list of all the heights. It's this text case, it's this input. And our maxed area is 0. So let's just call it 0 for now. And and we'll replace the max area as we progress through the loop. So let's, so while our left index is, so now we're just doing one loop pass. While the left index is less than the right index, let's track the width. So as you may remember, the width is always, it's just the x-axis. So it's our right index minus our left index. And let's also track the height. So this is kind of, so the height is, the variable name has already been taken over by the input list. So I'm just going to call this like height number. Not the most elegant, but it is what it is. So here's the brain leap. We don't want the water to overflow. So remember, we want to take the minimum of the left and the right index that we're currently on. So we're taking, let's actually do the left index here. And then the height of the right. All right, so, and then as you remember from grade school, our area is the width times the height. Temp area, width times height number. So that gives us our area for the left and right index. And if the temp area is greater than the max area, we replace our max area by the temp area. All right, so now it's time for actually incrementing the pointers. So if our height of our left index is greater than the height of the right index, as I said before, if the height of the left index is greater, then we don't increment the left index because, okay, let's start from at the beginning of the loop. Index position 0. The height is 1. Now we're comparing it to the height at all the way at the right, which is which has a height of 7. The integer value is 7. So 7 is greater than 1. So we would increment the left index by 1. However, if the height of the left index is greater than the height of right index, so when we increment the index position by 1, now we have a height of 8, and that is greater than 7. So now we actually have to decrement the right index. And then we shrink the solution set, we keep shrinking the container size until we find so we try for all those combinations as we shrink. And then if we find a temporary area that's greater than a max area, we replace the max area with the temporary area that's greater. But you can see in this example that all we have to do is just literally increment the left index by 1, and that would give us our max area for this particular example. But for the other examples, we may have to keep shrinking and shrinking until we find the container with the temporary area with the most area, or with the most water for this example. So we just, so we reduce this by, I've been playing a lot with C++, so I thought you could do some kind of fancy code snippet, but I guess we're still in Python land here. So else left index, so else, let's say the height. So just to really make it obvious, the height of the right index is, in every case when the height of the right index is greater than the left index, then we know we need to increment the left index by 1. So, and then we would just return the solution, so that's return max area. So yeah, so we have one loop. So in terms of analysis, what's next out of range? So that's, so, oh yeah. Remember, the length of the height is out of range. We always have to, because we always start at index position 0, so we have to decrement the right index by 1, so we actually start here instead of the 1 over. All right, so this we're having a wrong answer here. Our output is 8, and they're expecting 49.
We're turning while in a while loop.
Yep. So we just have to do playing with Vim in LeetCode is not all right. All right.
What you're doing?
Yep. Yep. 49 is expected. So yeah. So we all for this particular input we're just incrementing the left index by 1 because the height of the right index is greater than the left index. So 7 is greater than 1. So we increment from 0 to 1 in terms of index position, and then the loop keeps going through each of the possible solutions. So let's actually let's print out the temp area to see what the loop is doing. But in terms of, yep, you can see that the loop is shrinking the container size accordingly. If the height of the left index is greater than the right index, it's going to keep shrinking the container box. But you can see that almost at the very beginning, the 49 is the biggest temporary area. So we're going to keep the temporary area as the solution set keeps shrinking, and then we end up with 49 as the biggest area. So let's also submit this. So the reason why they call this approach a greedy algorithmic problem is that because we're at each point where we find a locally optimum solution, and then we keep trying to traverse the possible solution space in the hopes of finding a global answer. So that's just a very fancy way of saying we're tracking a temporary answer, and then once we find, and if this temporary answer does turn out to be the optimum solution, then we can pat ourselves in the back. But if not, we're going to replace this temporary area. And for analysis purposes, because we're only doing one loop, instead of doing the brute force solution of an outer loop and an inner loop, our solution is O of n is linear time. So yeah, and this is an example of a greedy problem. So yeah, any questions?
I have a question, Evan.
Yeah.
So yeah, obviously you started by highlighting the brute force solution, which if you try to submit it, it times out, obviously, on some of the bigger arrays. Let's say you never saw this problem before, you're in an interview, you never saw it before, and you're presented with this, you don't have the sort of fancy graphic that was in the email body that sort of just shows you the solution. How do you make the intuitive leap from the brute force solution to realizing that you can go, you can sort of take the bounds of this array and then step in, so to speak, and I guess skip over some of those brute force solutions that essentially like you're discarding, you're not considering them. Does that question make sense?
Yeah. So yeah, I would always recommend implementing the brute force solution first, because that you should always implement the brute force solution first with the outer loop and the inner loop, and then you can always you always don't want to premature optimize. So always start with the naive solution first, and then think of ways of how to optimize the problem. So I think a lot of the intuition in terms, once you have the brute force problem, like the intuition I've always done is that if you always have an outer loop and an inner loop, and I've seen enough problems that there's always a way of doing it. Well, not always, but usually there's a way of doing it in one loop, but you have to use pointers. And so we use a left index and a right index here, and these are essentially pointers or counters. So, and then that's how you would exactly do it in one loop. So like I've just gotten that by experience, but in terms of trying to think of like an intuitive leap of logic in terms of making an outer loop, of trying to break down an outer loop and inner loop, I think I think the brute force solution is you know that you're doing a lot of waste because you're recomputing things that you've already recomputed before. And what I would think, if I haven't seen this problem before, is that is there a way of preserving, of knowing that, wait, this is the maximum area, like of drawing this particular problem out and say, okay, this is the temporary area or the container with the most water, and in my while I loop through the input list, is there a way of just realizing that, oh wait, all I'm doing is just incrementing the index position by 1, but I'm not decrementing the rightmost index at all. So I'm just preserving that order, and then I'm stopping at this particular point in time. And that's really what the greedy algorithmic approach is that forget about the future recombinations. Let me just step in this particular point in time. I'm starting with index position of 1. The max area is not going to be any big, but once I increment the index by another one, and now I can see that the max area is 49, and it's not going to get any bigger than this for the rest of the traversal of the solution space. So, is there a way I can keep track of that so that I don't have to keep trying to brute force and trying to find the remaining combinations for this area among all the other areas in the problem? Does that make sense? In terms of just like, okay, I've already found a locally optimum solution very early on, so I don't have to keep trying to make as many crazy combinations in order to find the maximum area. But I would say it really like comes with practice in terms of just realizing, okay, I have an outer loop and an inner loop. If I want to do it with one loop, I have to use some kind of pointers. I have to use some kind of tracking variables.
Can I also offer a suggestion? So one of the things that I think is super powerful about the solution is that we basically broken it down to the area is the width times the height. And then you've created some sort of structure around how you're going about the width, right? You start at a maximum width, and then you start decrementing the width by 1 at each iteration, right? So if the width is only going down, the height necessarily has to go up, right? And so that's what the if statement is making sure that the height is going up. Otherwise, if neither of those, if the height isn't going up, you know that possibility isn't going to work out. And so oftentimes we're given problems like this, and then it's sort of about playing around with the kind of values and trying to be able to fix one of the variables in a very structured way. In this case, it's the width, and then letting the other variable, the height, be very dynamic, and that's the actual thing where you're doing the map on the height. But your width is very much defined by the way you're solving the problem.
That was a pretty good explanation, Matt. Thanks.
And I also like, if you're in an interview and you don't solve this, like when you presented this problem, I didn't have an immediate intuition on how to solve it. And I don't know if you had like an hour-long interview, if there's like a definite way to get this. I feel like it's sort of, in the interview process, it's sort of think out loud long enough and say enough things out loud that they know that you can at least think about problems well, and then eventually they'll kind of guide you along to make sure you got to take the next step when you get to take the next step.
Yeah, and like in an interview setting, nobody is going to expect you to whip out like a linear solution, but they do expect you, or at least I would expect you to be able to at least whip out the n squared solution without much guidance. Like, oh, let me start with
the sliding window one.
Yeah, but let me start. Well, yeah. So like I'm starting out with, okay, I'm at index position 0. I have height of 1. Let me compute the area between this and this. Let me compute the area between this and this. And then as you keep, and then let me compute the area between this and 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 this. So then you should already be thinking, oh wait, that's just an inner loop. And then I'm storing all these temporary areas for my height of 1. But now let me try, let me go to the next height, and then let me compute the area between this and this. this and this, this and this, this and this and this and this. So like that is something that is expected for you to solve the brute force problem. And then once you solve the brute force problem, they'll probably ask you, is there a way of doing this more efficiently? And then they'll guide you with using of tracking using pointers. Yeah. So that is the yeah. So that's the. This problem is very familiar with the so. Let me.
I was gonna ask, is there like a name for this strategy? I just feel like I've done this in more than one LeetCode problem.
Yeah. So this is literally the first problem LeetCode is the two-sum problem, and you can see that the brute force problem is always outer loop and inner loop, and then like as you make it more efficient, now you're using like hash tables and you're doing it in a one-pass hash table, so you're just doing it with one loop. And there's a mathematical trick where you're tracking the diffs and then storing it in your dictionary, and then you'll be able to do that in O of n solutions. So so that's like the. So every time we try to find out a way of trying to make an O of n squared solution to an O of n solution, it's really using trackers. So the two-sum problem uses dictionary to track your differences, and for this problem of container with most water, it's just using the left index and right index variables as like a mini dictionary. It's not really like, but it's just a way of keeping track of your most efficient points at that particular point in time. So I would strongly recommend reading more on greedy algorithms. Greedy. I used to work in finance, so I'm a big fan of these. But yeah, that's it. If there's no other questions for me, I'm gonna hand it off.
Evan, I think you had a question about like what type of problem this is.
No, I was just asking because like sometimes I feel like with LeetCode, the only way to learn them is to kind of like do them, and then you just kind of start noticing the patterns that apply to maybe more than one problem. And I feel like in this case with the pointers, keeping track of the left index and the right index and only incrementing one of them, it's like a common strategy for LeetCode problems that you might encounter. It's worth just like knowing the strategy, I guess.
Yeah, exactly.
Yeah, I found that a lot of this stuff is just good old standardized test cramming, and just do a bunch of these. Eventually, you just start seeing them. This is a finite field of these kinds of problems that they can give you. They'll change around the details of it, but the problems they tend to give you are within a specified set.
Yeah, it's really there's really just practice using it's just really extensions on core patterns and algorithms and design and data structures. So once you do enough of these problems, if there's a novel problem, you're just really extending a core data structure, algorithm, or pattern in a different way. But that's typically all the problems we've done so far are typically just extensions of classic patterns that are tested over and over again in LeetCode.
And can I ask you a quick question as well?
Yes.
So I just started studying the data structure and algorithms, so I'm really at really junior level, and then I started a LeetCode problem as well for the very easy ones. But my concern and then my difficulty is that like when I read the question that I cannot, maybe I'm not familiar enough or I digested the concept enough, so like I cannot think about what strategy to come up. You recommend to practice and then see the solution first, or like just like take some time and then like dig into like find a solution as much as possible. What is the like most efficient way that I can achieve this in a very short time?
Yeah, I would say practice for like like 15 minutes, and if you don't know what to do, I would just look at the solutions.
Mm.
Yeah, because a lot of the solutions are just because a lot of because these problems are not novel and the solutions are well established in terms of using an already proven algorithm or data structure or pattern, but just extending one of those classic patterns. So when you look at a solution, you actually will be learning, like, if you haven't seen it before, you'll just be learning one of the classic approaches, and then you'll see them how they squeeze it into the problem. So I would just look at the solutions after like 15 minutes.
Okay, good.
But then I would keep it in the backlog and then like review them like after a week from scratch and see if you still if you remember the pattern at hand. Yeah.
I see. Okay.
Yeah. But yeah, that's the. So let's look at the solutions here. Wow. Wait. Okay. I didn't realize they have a solution in LeetCode for a pre-written solution. So not all LeetCode problems have like a pre-written solution, but this one does. So okay. Yeah, it's very similar. Max area equals max area min height. Yeah. Yeah. This max is just like, that's cramming way too much stuff into one line. So I prefer my approach of, I think it's a lot more intuitive that the temp area is literally just the width times the height, and the height. And just seeing that the height is the minimum between, we don't want the water to overflow, so we want to make sure that the height is the minimum. So you don't have to worry about taking the max of a min. It's just like, I think the solution is not very readable. But here it seems very similar. So yeah, so as Evan said, yeah, there's always a brute force naive answer, and then there's like a way of doing it in one loop, and by doing it with one loop, you always have to keep track of using pointers, which is a fancy word of like, like as I said in the first problem of LeetCode, it's like the two-sum problem, and the two-sum problem is literally the same exact pattern of keeping your solutions. The brute force is always outer loop, inner loop, and then the most efficient solution is just keeping your answers in a dictionary. Which is essentially keeping pointers. Is there anything else?
I'd want to touch on that a little bit. So I think if there's like two different hurdles that you might be having trouble with, one is like coming up with the brute force solution, and the other is coming up with the optimal solution. And if you're having trouble coming up with the brute force solution, I think the problem might be the language. Part of like getting used to computer science and software in general is like learning how people phrase problems. And so I think if that's what you're having trouble with, I would definitely be looking at the solutions and even try like going the opposite way. Like take an algorithm and try writing it as a question. And I think that might make you more comfortable with how computer scientists think about these problems and how they word these problems. And then if you're having trouble with like coming up with the actual optimal problem, honestly, that just sometimes just takes an epiphany, and there really isn't a clear answer to that. And so I think wrestling with the problem is oftentimes, like some problems you wrestle with for a long time. Sometimes you come up with a solution very quickly, and so like being patient and having like lower expectations, I think is definitely helpful, because we see Edwin kind of come here week over week, come here and present a solution, but a lot of these problems, if any one of us, even the senior engineers here, were kind of taking it off on the first time, it would take us the kind of like eureka moment. So I would definitely make sure to have like, don't think that you need to be solving these problems immediately or having like, oh, I know exactly how to solve it.
Yep.
Good point.
Yep, that's it for me.
Okay.
Thanks, Edwin.
Yep.